In this video, we're going to take a look at the role of chirality in creating and producing different medications. So to remind ourselves, chirality occurs when we have four different groups of atoms or groups that are attached to a single carbon atom. And so when you have a chiral center, you're going to have two stereoisomers that are mirror images of each other, otherwise known as enantiomers. So in terms of chirality in drugs, what's really neat is enantiomers can behave very differently in the body as a result of their different shapes. And so, for example, if we take the enzyme active site here, and we have one enantiomer coming in and binding, the stereochemistry works so that A binds with A, B binds with B, and C binds with C. And that's the active enantiomer, and that's what needs to happen. But if you had its stereoisomer, it would come in and bond A with A and B with B. But because of the chirality and the flip in terms of the mirror image here, D would line up with C, so no bond would form there, making that the inactive enantiomer. So chirality does really play quite an important part in terms of how the different enantiomers can behave in our body. And we saw that with thalidomide. So thalidomide is if you recall, a morning sickness drug that was given to pregnant women to combat morning sickness. And it was given as a racemic mixture, which means it had both forms of the enantiomer in the mixture in equal amounts. And so one of the enantiomers that was found after some time was responsible for causing birth defects. So the one enantiomer here was responsible for birth defects, whereas the other one here is perfectly safe. And if we look, our chiral center is right here. Okay. So can make a huge, huge difference in terms of even the safety of different drugs within the body. Now, in terms of making just a single enantiomer in drug synthesis, can be tricky, but it can be done in a couple of different ways. The first is to synthesize a racemic mixture and then follow that by a separation technique called chiral chromatography. The second would be using something called a stereoselective. So stereo means like specific stereoisomer selective or asymmetric synthesis type of pathway. And so this would be a synthetic reaction that's used to selectively produce just one of the enantiomers. A way that we could do that is we can use something called a chiral auxiliary. So what is a chiral auxiliary? Well, it is the definition, one enantiomer of an optically active substance that's temporarily incorporated into a non-chiral molecule to produce that single enantiomer of the product in a synthesis reaction. So if we take, for example, this molecule here, and we add in a chiral auxiliary to this hydrogen here, then essentially we're holding the rest of the molecule kind of in place so that if we have a reaction now happening here, we're going to create just one specific type of enantiomer. And then we can remove this chiral auxiliary to basically regenerate just the hydrogen there. So it's essentially something we add on in the synthesis process to lock the molecule into one sort of particular shape or conformation so that we can get the kind of enantiomer that we want in our synthesis, and then we can remove it to restore the molecule in the synthesis pathway. Taxol is a great example of using this sort of synthesis with a chiral auxiliary. So let's talk about Taxol and what it is first. It's a type of drug that's used to treat many different forms of cancer, mostly breast cancer, but also ovarian and lung cancers. And it's given as a part of a course of chemotherapy, and this is done intravenously through an IV. The way this drug works is it acts by preventing cell division. So it does that by binding to microtubules in the cytoplasm, and that prevents them from breaking down during cell division. So essentially disrupts the cell division pathway. You should take a look and find chiral centers in Taxol. If you want to, pause the video here, try and find them, and then you can continue on watching. Okay, so like I said, the synthesis or semi-synthesis of Taxol does use chiral auxiliaries and uses them quite effectively. I'm just going to write chiral aux because I can't think of how to write auxiliaries. So Taxol was originally obtained from Pacific yew tree bark. However, it takes a lot of tree bark. It actually takes the bark from more than one tree to provide enough Taxol to treat one patient. And so you can imagine it takes a very long time to grow a tree to maturity to be able to then harvest the tree bark to be able to treat a patient. So we'd never be able to keep up if we were using just natural resources. So a semi-synthetic process was developed that involves making Taxol from another natural product derived from the needles of the yew trees, which there are lots. And so we're not now limited by how much we can produce. And we use a chiral auxiliary in this semi-synthetic process. So the advantages here are that it can be made on a large scale and it reduces the environmental impact of this particular synthesis process. So that is just a quick glance into how chirality works in drugs and how we can create specific enantiomers in synthetic pathways. That's it for this video. We'll see you in the next one.